Hello everyone and welcome to Mass Analytics Marketing Mixed Modeling Masterclasses. Today's course is going to be about modeling, and we have 4 parts in the modeling course. The first one would be an introduction to regression analysis. The second one would be about model selection. The third one would deal with data calculation or contribution calculation and ROI calculation. And the fourth one will be dedicated to advanced modeling techniques, like, for example, nested modeling, log linear, and pooled regression. What we have seen so far is how we collect the data, what data we collect, what are the hints to follow in order to explore the data that you have collected, and also how can you create additional variables in order to improve the quality of your model. And let's start now with a quick introduction of regression correlation analysis. Today's course is split into 4 parts. The first one is going to be about correlation. Then we'll be looking at simple linear modeling, then multiple linear regression, and fourth and last, we'll be looking at overall model evaluation. We have now moved to the 4th phase of our marketing mixed modeling workflow. We are in the stage of model building, where we are meant to create our model, compute our ROI and also our contribution, and report on all the results and insight as part of this phase. Now, looking at the software master, all those capabilities of model building, contribution calculation, ROI calculation, extraction of results are present into the module model. Correlation, or Pearson's coefficient of correlation, is a key statistic to be computed as part of your MMM project. So what does it mean, correlation? It's actually a measure of strength of an association between 2 variables. So if we compute the correlation, it is a metric that generally ranges between -1 and 1. So if we are close to the edges, that is either 1 or -1, we can talk about a strong association between 2 variables. If we have a value that is more around 0 or a little bit higher than 0 or lower than 0, then we are talking about weak to medium-sized correlation. I would like to insist here that correlation is a measure of association, and it's not necessarily a measure of causation. For example, the number of people drowning in the sea and the sales of ice cream or soft drinks in summer are highly correlated. But that does not necessarily mean that there is a causation here. So eating ice cream or drinking soft drinks during the summer doesn't necessarily lead to people drowning in the sea. But rather, there is a third factor that is actually summertime, it's hot, and hence this is what is causing the 2 variables to move towards the same direction. Also, correlation can only depict linear association, and it fails to depict any nonlinear associations. Regression analysis is an advanced data analytics technique. It is about depicting a dependency relationship between 2 variables or 2 sets of variables. The very first set is called dependent variable, and the second set would be your independent variable or your predictors or your explanatory variables. So you would be using your explanatory variables in order to predict the outcome of the dependent variable that is of a metric nature. Let's explore the mathematical formula of a simple linear regression. Here, we have a relationship between 2 entities. The first one is y, which is also your dependent variable or your outcome variable, and the second one is x, which is also called your independent or your explanatory variable. Now, we have only 1 variable in this equation inside the explanatory set, and that's why here it is called a simple linear regression. If I had more than 1 x inside the set of my explanatory variables, I would be calling this a multiple linear regression. Now, let's look at the other parameters. Beta 0 and beta 1 are the parameters to be estimated. They are unknown, and what we will try to do is to estimate those parameters. Beta 0 is also called base or intercept. Beta 1 represents the coefficient of the variable x. Now, the last part of the equation is actually the error term, or also the residual. What we want to achieve in any regression analysis is to make sure that the error term is random and is not influenced by any other factor, and the portion that is explained by the error term is as small as possible. So most of the variations that you observe in your y or your dependent variable are captured by the regression analysis that you are undertaking. In other terms, this equation is about telling me that if you give me some information about the movements of x, I will be capable of refining my forecast to you when it comes to the movements of the variable y. And that's what a regression analysis is about. Example, what is the impact of advertising on my sales? Or in other terms, if I know how much budget I'm investing on advertising, am I capable of forecasting how much sales I will get? Actually, a simple regression analysis can allow you to do that. And the idea is that you will collect data about your X, which is here your advertising spend, and your Y, which is here your volume sales. And using that data collection, you will use the regression in order to estimate the coefficients beta 0 and beta 1. Once these are estimated, then we can easily tell you what are the level of sales that you will be achieving if you invest a certain amount of money on advertising. Obviously, subject still to that small error term that obviously we cannot eliminate. So how does it work, right? So taking the example of earlier on, we have collected data about advertising budget and sales data for a number of weeks. What we have also done, we have plotted this data set. So each point represents a couple whereby you have an x coordinate and a y coordinate. X represents the advertising budget and the y coordinate represents the sales that have been achieved in that particular week. Now, the way we can understand better the relationship between these two variables is about trying to find out what is the best line that can go through all the points that you can see in this chart. Basically, what we are after here is to find out the line that fits better and that goes through all the points that you can see in this chart. So that green line is called your estimate and is also called y hat. And if you project any data point on that particular line, you will obtain your estimate. And your fitted line equation is actually y hat is equal to beta hat 0 plus beta hat 1x. Note here we are not talking anymore about beta 0 and beta 1, but rather their hat variations, because here we have estimated the parameters beta 0, beta 1 using beta hat 0 and beta hat 1. Now the intercept is where the green line intercepts your y-axis, and that would represent your intercept or your base sales. The slope will be actually the slope of the curve of your fitted line. Now, if we take any data point in here, it's represented by two coordinates, x, y, and yi. If you project that particular point on the line, we will obtain the estimate of that particular point that is given by y hat. Now, what the difference between the position of the point and its projection on the line, which is represented here by the dot in yellow, represents the error term. Obviously, the smaller the better. Yes, here we try to fit a line between the different points, and we know that sometimes the error terms for some points is small and for other points is rather big. And the idea is that to fit a line that goes through all these points while minimizing the distance between the point itself and its projection on the line, that is also called residual. OLS, or ordinary least squares, is actually the method that we apply in order to find out or to estimate the parameters beta 0 and beta 1. And it's actually about trying to fit a line that goes across all the different points while minimizing the distance between that line and the different data points that we have seen in the chart. So minimizing the error term for all the points that you have in your chart will lead to the solution of the problem and will lead to the estimation of beta 0 and beta 1. Let's now talk about the decomposition of the variance into two components, the unexplained and the explained part. Imagine that your boss comes to you and asks you about estimating the sales for the next year. One of the simple methods that we can use is to look at the average sales for last year and then use that as a forecasting for the sales that will be generated in next year. So a simple forecasting method would be based on the average. Now, if we use regression, we think that we are using a little bit more sophistication into the methodology. And in the regression analysis, the idea is that if I receive information about how much budget I'm expected to spend next year, I'll be capable of refining that forecast about the sales that I will be achieving next year as well. But let's look at how much gain I have when I use regression over the simple method of using the average. So the difference between the projection of a specific point on the green line would represent your estimate. And the difference between that and the yellow line would represent what I would gain when I use regression in order to do my forecasting. Now, the difference between the real point, which is the red point here, and its projection on the yellow curve represents what we call the error earlier on, or the residual. Where we want to be is to be in a situation where the sum of squared error, or the residual part, is very small compared to the SSR, which is the sum of squared regression. So in other terms, I would like my regression line to explain as much as possible, and that my error term represent a small fraction of the total variance. So what we have achieved here is that we have decomposed the total variance, SST, sum of squared total, into two components. The first one is what is explained by my model or my regression line, which is represented here by SSR, which is what I gain on top of a simple method based on the computation of the average, and the SSE, which is the sum of squared error, which is the residual part or the unexplained part of my equation. This discussion about the decomposition of the variance between sum of squared regression and sum of squared error, or the portion that is explained and the portion that is unexplained, yields us to introduce one of the key statistics that is computed as part of your regression analysis, which is the R-square. So what does it mean, R-square, and what is the definition of it? So the mathematical formula of the R-square is simply the SSR divided by the SST, which means that you take the model and the portion of the variance that is explained by the model, and then you divide it by the total variance that you want to explain. So what then you obtain is that the coefficient of determination R-square would represent the portion of the variance that is explained by the model. In the example of earlier on, if we obtain, for example, an R-square equals to 70%, that means that 70% of the variation that I see in my sales data are actually explained by the movements in my advertising variable. So advertising is capable of explaining 70% of the variation that you see in your dependent variable or in your sales in this example. And that's why actually R-square is very important, because it tells you in a way how good is your fit and how much your model and the variables that are inside your model are capable of explaining the variations in your KPI. Continuing on the series of the key statistics that needs to be computed and produced as part of your MMM project, I'm going to introduce the standard error of the estimate. So actually it's a measure of accuracy of your model. And how it is calculated is simply some kind of an average of the error term that you are making when you are predicting your values. So you take this residual that we have looked at earlier on, which is the difference between your real point and the projection on the line, and then you take the average of those residuals, and that would give you an average error term that you are making with your prediction. And that would be a good statistic that needs to be reported as part of your MMM project, because it will tell the people that are around you how accurate are the results of your modeling, and therefore the results of your prediction in the future. So the last thing that I would recommend you to do as part of your regression analysis, once you finalize your equation, is to actually analyze your residuals. Again, your residuals is actually the difference between your real data point and the projection of that data point on your regression line. And the difference between the two would be the error term that you are making, the average of which will be helping you calculate your standard error of the estimate. But also it's very important to look at the characteristics of this residual term, because to apply OLS, ordinary least squares, your variables should satisfy certain conditions. And by you observing the behavior of the residual term, it will help you better understand and better make sure that what you are doing is right. For example, your residuals needs to be examined, and you need to find out and check whether your residuals are linear, whether they have a constant variance, whether they are normally distributed, and whether they are respecting the independence condition. Multiple regression. What we have seen so far is the simple linear regression, where we have only one variable explaining the movement of another one single metric variable. Multiple regression is as simple as saying the movement in the dependent variable are not anymore explained by the variations in the movements of one single variable, but rather by the movements of many other variables. So when we start adding more variables into the regression equation, we move from the simple regression analysis to the multiple regression analysis. For example, in a typical marketing mix modeling project, we are faced with many variables that could impact the sales performance. A typical example is to say that my sales data is impacted by my media investments, my promotional activity, my seasonality, and my distribution variables. So in order to be capable of measuring the impact of those variables on my sales, I need to construct a model. And in this model, we will have 4 variables influencing the movement of my sales. So why my sales will be a function of, obviously, your base, which is constant, or your intercept. In addition to that, we will have the incremental impact of your advertising budget. In addition to that, you will have the incremental impact of your promotional activities. Added to that, you will have the incremental impact of your seasonality and also your distribution. So the term beta 1 x1 actually represents the contribution of your advertising on your sales. The term beta 2 x2 represents the contribution or the impact or the incremental sales that you will be getting as a result of you investing in promotions. And this model will help you better predict your sales performance. So in another scenario, you can tell me, okay, look, I know how much budget I should be allocating next year. I know what are the promotional mechanics I will be using next year. And also I can tell you what is my distribution level, and I can also forecast a little bit the movement of seasonality. Based on that, are you capable of telling me what are the incremental sales that I will be getting? This becomes very simple because once I estimate the parameters beta 0, beta 1, beta 2, beta 3, and beta 4, then I can easily plug in the values that you have given me, and I can predict to you what are the incremental sales that you will get as a result of that. But how can we estimate the parameters beta 0 all the way to beta 4? Exactly the same way as we have done it earlier on with the simple linear regression. The idea is still the same. I'm going to try to minimize the residuals, which is the difference between y and y hat. And solving for this problem will give you the estimates of beta 0, beta 1, beta 2, beta 3, and beta 4. And the method of estimation is still the same, ordinary least square, that looks at finding out the best solution that will minimize the error term across all the data points that you have collected as part of your data request. Now that we have run our OLS analysis and then we have estimated the parameters beta 1, beta 2, beta 3, and beta 4, how can we interpret those estimates? For example, the coefficient of your advertising variable would simply represent by how much your sales will move if you increase your X by 1 unit or your advertising budget by 1 unit. while keeping all the other variables at the same level. That is, your seasonality stays the same, your promotional activity stays the same, and your distribution activity stays the same. So the coefficient in the context of multiple regression is also commonly called a partial correlation coefficient because it tells you by how much your dependent variable will move as a result of the movement of that independent variable while keeping all the other variables at the same level or constant. The other thing that I would like to insist on is when you estimate your coefficients, you need to make sure that they are reliable or robust. One way of checking the robustness of your coefficient is to look at the t-stat that is associated to this particular coefficient. And as a rule of thumb, if we have a coefficient estimate whose t-stat is above 2, we consider that the measure is reliable and therefore we can use it for prediction purposes because we are quite confident that actually the coefficient estimated is sufficiently departing from 0 to build a forecasting scenario onto it. Model evaluation. In this slide, I try to summarize the key statistical metrics that you need to compute as part of your MMM project in order to evaluate your model. I will start by the first one, which is the coefficient of determination R-squared. As we have explained earlier on, this metric helps you understand what is the portion of your total variance that is explained by your model. For example, in the context of the regression equation we had earlier on, if the R-squared is equal to 85%, it means that 85% of the variation that I see in my sales data is actually explained by media, promotions, distribution, and seasonality. The second metric that I'll be talking about here is the F-statistic. What the F-statistic will help you do is to find out whether your model is statistically relevant or statistically robust. And H0 that is related to this F-test is that all your coefficients are equal to 0 at the same time. In other terms, taking the example of earlier on, we are testing whether all the coefficients of media, promotions, seasonality, and distribution take 0 at the same time. If it is the case, it means that overall my model is not significant. If it is significant, it means that now I need to test every single variable statistically and separately. So succeeding the F-stat doesn't mean that every single variable in your equation is significant. It rather measures whether overall your model is significant. That's why we need to move to the third statistic that you need to compute, which is the t-stat. The t-stat is computed at the level of the variable. For example, I will test whether my media variable is significantly different from 0. And for that, I will run a t-test. If the t-value that I obtain is greater than 2, as a rule of thumb, it means that my variable is statistically significant from 0 and different from 0 if I am using, for example, a 95% confidence interval. Now, the t-stat is actually the ratio between the computed or the estimated coefficient and the standard deviation or the standard error of the coefficient. And the bigger the t-stat, the better it is because it means that your coefficient is statistically robust. The fourth one is actually the standard error of the estimate. Remember when you talked about this one, it's actually some kind of an average error or an average residual of all the residuals that you have created or that have resulted from your model. And obviously the smaller this metric, the better it is because it means that overall the average error that you are making through your model is actually controllable and is of a small size. Now, the other three metrics that I want you to compute are first the Durbin-Watson, which is linked to the fact that we want our error terms or our residuals to be independent from one another. So you need to run the Durbin-Watson test in order to make sure of that. The second one is about the multicollinearity, or in other terms, whether my independent variable or my explanatory variables are correlated. because in regression analysis, we do not want our explanatory variables to be correlated. To do that, you can run the variance inflation factor or the fifth statistic, and you would want that fifth statistic to be under 5 for every single variable. If it is not the case, it signals that you have a problem of multicollinearity, in which case you need to remedy to that. The last statistic that I would advise you to compute is the Jack-Bera or the kurtosis or the skewness, which are all measures that help you test the normality of your residuals. Because at the end of the day, we want our residuals to be randomly distributed, normally distributed, and non-correlated. What I talked about earlier on is establishing whether your model makes sense statistically. However, remember that marketing mix modeling is about modeling consumer behavior. So it's very important to make sure not only that your model makes statistical sense, but also it's very, very important that your model makes commercial and business sense. For example, if I am modeling a CPG brand, it is not possible to accept that price has a positive impact on my sales. In other terms, can I go back, present my results, and say that the higher the price, the higher the sales? That's counterintuitive. Another example, if I am spending $20 million on advertising, and my model says that I have a negative coefficient of advertising, I really need to dive deeper and deeper and deeper and try to make sure that I'm doing the right transformation and that actually this is something that I am capable of defending. Because going back to your client or your internal teams and telling them that actually advertising makes you lose sales is something that will be very, very difficult to accept. So please make sure to wait a little bit, look at your equation, and not only look at the statistical robustness of your results, but it's very important to judge whether the level of elasticity, the level of the seasonality, the ROI, and the different parameters that you are estimating make sense commercially, business-wise, and you are capable of defending them in a very easy way when it comes to presenting your results back to the client or back to your internal teams. Next course would be about model selection. So see you in next course.